used in the industry, primarily oil and gas industry. Reciprocating pump has a very important role to play in the oil and gas industry, especially with the upstream side of businesses where we have exploration, production, and completions. This pump actually plays a very important role, still does play a very important role. And this is to give you an idea and flavor of how these pumps are playing a role in securing our energy requirements. So the agenda is just quickly going through it. We will quickly describe what the operating principle of the reciprocating pump is, different type of the pumps, what are the working principles, how the work is done by the reciprocating pump, how the flow rate is calculated, how the work is calculated, and we will conclude the presentation on a concept which is known as the slip in the reciprocating pump, which kind of determines the efficiency of the reciprocating pump as well. One thing which I want to ensure is that the topic is very much centered around the reciprocating pump. There is a very similar concept which is called reciprocating compressors, which are more focused towards gases and superheated fluids. This would not be centered around that. This is more centered around the fluid part of the work. Compressors is an entirely different topic, but some of the concepts that you will learn over here, some of the constructions of the reciprocating pumps which you will hear over here is very much applicable in the reciprocating compressors as well. So essentially, reciprocating pump has a couple of different components. There is an intake pipe which is immersed in the reservoir. The intake pipe is where the fluid will travel into what we call a cylinder. In the cylinder, we have a piston, just like what you will see in your car. There is a connecting rod or a piston rod, which is connected to a crankshaft. All of it is actually enclosed in a cylinder, and then you have a discharge pipe. This is the most simplest construction. These are the components. These are the things that you will see in any reciprocating pump. So it is essentially a hydraulic machinery, which is there to serve one purpose only, which is to convert mechanical energy that is provided by a prime mover into hydraulic energy. And the working principle is that it works by sucking the liquid into a cylinder, which contains a reciprocating piston, just like your car, in which the mechanical force, which is a thrust force, is exerted into the liquid, which increases its hydraulic energy. And by increasing its hydraulic energy, increases the pressure of the liquid. So the reciprocating pump is there to transfer fluid from one place to another by increasing the pressure of the fluid. So that's why in very high pressure applications, you will see a reciprocating pump and not a centrifugal pump, just because although centrifugal pumps do provide us with pressure increases, a pressure increase of the fluid, as well as high flow rate, but it does not provide the same pressure increase that you would require for your application. It is also called a positive displacement pump. So whenever you will heard about the positive displacement pump, just picture as a reciprocating pump. And a positive displacement pump can have a piston pump or a plunger pump. The piston is actually present in the cylinder, in which a reciprocating motion, that means a back and forth motion, will be converted into hydraulic energy. It is primarily used in places where there is relatively smaller flow rates required, smaller amount of water on any fluid, which needs to be developed at a very high pressure or a very high head. So just whenever you are picturing a high pressure application, whether it's in a petrochemical plant or a refinery or a chemical establishment, that's where you will see a lot of reciprocating pumps. There are essentially three types of reciprocating pumps. The first one are called piston pumps. These are very commonly used in the industry. We will see one example of the piston pump in the following slide, in the coming slide. There are plunger pumps, and then there are diaphragm pumps. Piston pumps can be two types. One is called single acting and double acting. We will talk about single acting and double acting in coming slides as well. Essentially, single acting is that you will have one suction stroke and one discharge stroke. So in one back and forth motion, when the piston will move in one direction, there will be a suction, and when it will move to the other direction, there will be a discharge. Then there are plunger pumps. Essentially, plunger pumps also work on a similar principle as the piston pumps. You will have a suction stroke and you will have a discharge stroke. But the only thing is that it has a high pressure seal, which you can see right over here. If somebody can see, there is a red stationary seal. And then what happens is this is a stationary seal. It's a high pressure seal. It will ensure that the fluids will not leak into the environment across the cross section of the plunger. And the cylinder will slide through the seal. This makes sure that this pump can be used as at a higher pressure. People who have attended my previous lectures, we talked about the sucker rod pumps. Sucker rod pump is essentially a reciprocating pump, and it is a plunger type pump. So people who can remember that lecture, it was a rod or a plunger that was passing through a stuffing box or a stationary seal. And then last but not the least is the diaphragm pump. It is very commonly used in the chemical industry, especially as a dosing pump. It is used to inject chemicals, especially when you have to inject smaller or very precise quantities of chemicals. So we use diaphragm pump. Rather than a back and forth motion of a plunger or a piston, it uses a small diaphragm, which is essentially just a plate, a flexible plate. And with each stroke, it will do a suction stroke and it will do a discharge stroke. And one of the advantages of a diaphragm pump is very compact. It's very small. It can develop very high pressures in a very small compartment or a chamber. And it is a self-priming pump. That means you do not need to get the water all the way to the suction port. You can have a suction line which is completely empty, and it will, with each suction stroke, it will ensure that the fluid actually travels through the suction pipe into the suction valve and into the chamber. So it can run dry without any damage. A couple of common examples of the piston pump. You have seen this in the villages as well, or the places where the excess of water is limited through the municipal systems. This is very much example of a piston pump where we have a suction pipe and there's a check valve which will ensure this is essentially a suction valve, which will ensure that the water will travel in one direction. You have your piston rod, you will have your piston, and then with each stroke, it will let the water in the chamber, impart the hydraulic energy, and then at the discharge, it will ensure that it goes to the discharge line over here. Then diaphragm pump. This is just an example of a large version of the diaphragm pump. You will have a standing valve or a traveling valve, or what we call a check valve. It's a ball type of check valve. Suction side at the suction stroke, the ball valve will travel. The water will enter into the chamber. The energy will be transferred, and in the discharge stroke, the discharge valve or the check valve over here will open, which you can see in the second schematic, and it will ensure that the water will discharge into the discharge line. Very commonly used examples which you can see in your everyday life. Some of the major parts of the reciprocating pump, we have already talked about it. Essentially, your suction pipe, your suction valve, your cylinder, your crankshaft is right over here, your delivery valve or a discharge valve, and then your delivery pipe. Essentially, in a lot of places where there is a huge amount of distance of the vertical height that needs to be traveled by water, you can see them very commonly used. And then air vessel over here. Air vessel is very important because reciprocating pumps, unlike centrifugal pumps, are self-priming pumps. So they can actually run dry. Not that you want them to run dry, but they can run dry. There are lubrication systems that are there to make sure that the sealing is properly lubricated, all the bearings are properly lubricated, and then the air vessel is there to ensure that it remains a self-priming pump.
Hassaan Ali, can you say that last part? Can you go back to that slide? The air vessel does what?
So air vessel is there to provide air. Essentially, it is a reservoir of water on the side. That is to ensure that if there is a air that is traveling through this suction pipe and a discharge pipe, it actually acts like a reservoir of air. So the air will be stored over here, but the water can't go into the discharge port.
Is there any way of releasing that air if it builds up too much?
Yes. So there is a pressure relief valve on top of this of what we call an air vessel, which after if certain pressure is built, the PRV will open it, will discharge air from the top. Yeah.
Thank you.
It prevents any overpressuring kind of a situation. When we will go into the examples of these pumps that are used in the oil field, you will see examples of the air vessels with the PRVs. So in the reciprocating pump, I talked about the single acting pump and a double acting reciprocating pump. These are more common in the piston types of pumps, not the plunger type of pumps. So in the single type of piston pump, essentially one stroke is suction and one stroke is discharge. While in the double acting pump, one stroke is suction and discharge. It's just that we will see there are two suction lines and two discharge lines. So with one stroke, it will act as a suction for one side and a discharge for the other side. And for the second stroke, it will act suction for the second side and discharge for the first side. So these can be characterized if you are looking at a reciprocating pump. If look for two inflow lines and two outflow lines. If you do see two inflow and two outflow lines, this is actually a double acting plunger pump, piston pump. This is just an example of the single acting one. You have one suction line, one discharge line. During the suction stroke, the piston will move backward. The water will enter into the cylinder through the suction port. And the delivery valve will remain closed. This is to ensure that there is no cross communication and there is no water that is being discharged through the discharge port in the suction stroke. Once the suction stroke is completed, the piston will move forward. When the piston will move forward, the force of the fluid will flap close the suction valve and it will open the discharge valve. When that happens, the fluid will transfer into the discharge line. So this is what we call a single acting reciprocating pump. In the double acting reciprocating pump, as I mentioned earlier, the suction stroke of one side essentially becomes a discharge stroke of the second side. During the suction stroke or the first stroke, I will not call a suction stroke because essentially it's not a suction stroke. In the first stroke, what will happen is that your piston is moving backwards. Your suction port of one side will open. The discharge port is remaining closed. But what will happen is that this fluid motion will actually open the discharge port on the second chamber. When that happens, the fluid from the other side of the plunger, you must remember that there is a sealing on the seal rings on the plunger, which will ensure that there is no cross communication of the fluids. So when the piston is moving backward, the discharge port of the second chamber will open, the suction port will remain closed, and then you will have discharge on the other line. So essentially, you have water entering into the first chamber and water is discharging from the second chamber. And then similarly, in the second stroke, what will happen is that your plunger will move forward or towards the left hand side. The discharge port on the first chamber will open, essentially acting as like a suction stroke on the second chamber. So you will discharge liquid into the second line and you will have the liquid enter into the second chamber. For the single acting reciprocating pump, there is a way to calculate the discharge as well as the prop power that is required. The formula for that is the cross-sectional area multiplied by N, which is the number of revolutions, divided by 60, which is you're trying to calculate discharge per stroke. In this formula, ALN, A is essentially your cross-sectional area of your cylinder. L is your length of the stroke. And then N is your number of revolutions. In the double acting one, what will happen is that you will multiply that with 2 because essentially you are doubling your discharge, right? Every stroke you are having a discharge, so multiply that with 2. And then if you are trying to calculate what is the work done or the power that is required by a single reciprocating pump. The formula for that is the weight of water lifted per second divided by total height through which water is lifted. So the total height that the water is lifted is your suction height and your discharge height. The weight of water lifted is essentially your rho GH, which rho is your density of water, gravity multiplied by your flow rate. You have already calculated flow rate in your previous formula. You just plug in the value of the flow rate over here, which is ALN divided by 60. And then you're divided by 60 because you calculated it per second, multiplied by your suction height and your discharge height. And essentially that is the work done that is required, or the power that is required for a single acting reciprocating pump. Now multiply the whole thing with 2. The 2 is you will have your work done by the double acting reciprocating pump. The work done divided by 1000, you will get your power required to drive the pump in kilowatt hours. Very simple formula, just plug in the value. Essentially what you need to require is the length of the stroke, the cross-section area of your cylinder, and your number of revolutions per second. And you can calculate your power required to drive the pump. Now this was, before this slide, we were talking about the basic scenarios or basic schematic of a reciprocating pump, working principles and type of reciprocating pumps. As I mentioned earlier, reciprocating pump is very much used in the upstream of oil and gas. It is used in 2 primary operations. One is called cementing and one is called stimulation of fracking. Both of these operations require very high pressures. So when we are talking about high pressures, stimulation can be done at the pressures of 10,000 psi or 15,000 psi. Now we are going to a point where stimulation might require 10 to 20,000 psi. This is a lot of pressure. If you open up your typical tap valve, your pressure is between 35 to 60 psi. The pressure in your tire of your car is 35 psi to 40 psi maximum. We are talking about 15,000 psi. We are talking about 20,000 psi. This is a lot of pressure that is required. And and you are very much aware that a lot of these oil and gas wells are very remote. You don't have access to power very rapidly. So you need something which is driven by essentially your diesel engines and your natural gas engines, because these are the 2 things that are available on oil and gas site very readily. Electrical energy is not very commonly used. However, with the quest to move towards zero net carbon emissions, a lot of operators are moving towards providing electrical power on site. If that is not possible, we have gensets on sites that can that can effectively make that lease self-contained or self-sufficient. So essentially what we are seeing in the market coming up now is that the reciprocating pumps, rather than being driven by the diesel engines or by the natural gas engines, they are being driven by the electrical motors. So that is new and upcoming. It is being trialed right now. Not trialed, it's still a very new technology, but people are adapting to it right more. So how the reciprocating pump actually works in the oil and gas site is slightly. I have a small video that is embedded in this presentation. We are just going to see the reciprocating pump in the real life in an oil field example. It will give you a flavor and it will let you appreciate how robust the technology is.
When you started your share screen, did you push that little button at the bottom to allow sound?
I don't believe so.
Yeah, because we don't hear anything yet.
There is no sound in this video.
Oh, okay.
Yeah. So this is a pump that is used in a stimulation and the cementing vessel. You can see your plungers moving back and forth right over here, your crankshaft right over here, converting or transmitting power to your plunger. There are 2 parts or 3 parts of it. of this pump. There is one which is called power end. This is what you call a fluid end. And essentially, these are your suction ports and discharge ports. You can see the crankshaft motion right over here. This is the casing of the pump. This over here, the shaft is actually connected through a gearbox or a gear reducer, and that gear reducer is connected to a prime mover, which can be a diesel engine or a natural gas engine. You can see the lines over here for the lubrication of packing as well as for the bearings. These are what we call pony rods, crossheads, and then this is what we call a fluid end. In the fluid end, you have your suction ports and your discharge ports. So this is a single acting pump. This is not a double acting pump. One thing which you will see is at the back stroke, you will have suction, and in the front stroke, you have your discharge. So you can see over here, when the plunger is moving towards the left-hand side, you will have your suction. It will fill up the cylinder. These are very high pressure valves. It will ensure that there is no cross communication. The plunger is moving forward, essentially opening up the discharge port, pushing the fluid through the discharge lines. And it will continue doing this, and it will continue doing this. What you want to do is essentially all the cylinders in this reciprocating pump. There are multiple cylinders. We are going to talk about them. In this one, there are, I think, 3. Essentially, you want to time it in a way that when one cylinder is doing forward motion, the other cylinder is doing the backward motion, and so on and so forth, so that there is like vibration that is being nullified or being cancelled. If all are moving forward or all are moving backward, we will have a very high vibration in the pump, which can actually damage the pump. And you ensure this back and forth motion through the crankshaft. So we were talking about the number of cylinders in the pump that is used in the upstream oil and gas industry. There are different number of cylinders, but most commonly we use what we call a triplex pump or quintuplex pump. Triplex means that there are 3 cylinders. Quintuplex means that there are 5 cylinders. Usually that depends upon your application, what is your discharge pressure, how much flow rate you require, and based on that, you will size up your pumping unit. These pumps can be mounted on offshore skid to go on an offshore platform, or on a trailer that is connected to a semi or a truck, which can haul it to the site. We were talking about the main components of the pump. We talked about the power end, we talked about the fluid end, and then third ones are called external drive and the gear reducer. External drive is essentially your prime mover, and your internal gear reducer is your gearbox, because your prime mover is moving at a certain RPM. You want to what we call reduce that RPM, because the prime mover is providing high RPM and lower torque. You want low RPM and higher torque. That is where your gear reducer will come in. Just a quick video right over here. There is no sound to it, but you can see this is your power end right over here. Your crankshafts, your pony rods. This is what we call a lubrication system. The lubrication system is there to make sure that all the moving components and seals are properly lubricated, because therefore there can be intervals where they are running dry, so you want to make sure that lubrication is there. So the power end is essentially the power end of the pump, which you can see right over here. This is called what we call a power end. You can characterize the power end because that would have the biggest diameter or cross-sectional area. The power end will have your crankshaft. that is essentially used to convert the rotational power into reciprocating power. It very much acts like the same way as the crankshaft in an engine. Um, the one of the things about the crankshaft, about the power end, is that this is your crankshaft right over here. You will have your bearings over here. You will have a breather. The breather is to ensure that because there is oil over here, if there is any overpressure kind of a situation, uh, or a huge pressure differential that is created, then the breather will allow the air to either come in and to kind of equalize the pressure. You will have your connecting rod right over here. The connecting rod is connected through a crosshead right over here to a pony rod. This pony rod is essentially the last piece of your power end, and that is connected. Pony rod is connected through a coupling to a plunger, and the plunger essentially moves in and out of fluid end, or the fluid end of the respirator. The power end lubrication system. The power end lubrication system is essentially provided by a lubricating pump. This lubricating pump is powered through a PTO shaft. The PTO shaft is called a power takeoff shaft. This is just from the prime mover. There is a shaft that is connecting. There is no special prime mover or a separate motor for the lubrication pump. It is run through the engine, through your auxiliary PTOs. The PTO is mounted on an engine or a transmission. There is a lube oil reservoir that is located at the very bottom of the pump, what we call a deck of the driveline. And this is to ensure that there is enough lubrication so that your power lubricating pump is always providing lubrication to your different moving components. One of the things about, as you can see, for any lubrication system, is to ensure that the reservoir is kept at the correct level. This is part of the preventive maintenance of the reciprocating pumps. One of the things which you will appreciate right over here is that there are a lot of moving components, right? They're moving at higher RPMs. There's a lot of pressure. There is a lot of conversion of the rotational motion into a linear motion. So these pumps do require a lot of maintenance. There's a very robust PM plan, or preventive maintenance plan, that is to ensure that these pumps are running at their optimal, and the reliability of the equipment is very much stressed upon, because you just cannot afford a failure. That's why on a lot of leases on which we have a stimulation or a cementing operation going on, you will have a spare or a backup pump. Going to the external components. In the external components, you will have something to ensure that you have, this is what we call a speed reducer. This is the input shaft. This is where your diesel engine or a gas engine will be connected to. It passes through a gear reducers, essentially your gearbox, and at this end it will be connected to your reciprocating pump. Essentially, what you want to do is that the torque and the RPM that is provided by your prime mover or diesel pump is very different from what you will actually require for your end application. For your end application, you want low RPMs but higher torque, because essentially you are transmitting that torque into hydraulic force. While your engine is running at a particular RPM, 1,000, 2,000, 3,000 RPMs, and it is providing low torque. So you need a gearbox in between to convert that low torque, high RPM to a high torque, low RPM situation. And so also the secondary function of a speed reducer or gearbox is to convert that or transfer that torque from the end of the shaft of the engine or a prime mover to your reciprocating pump. There are other types of external drives that are also used apart from these speed reducers. The other one is called a chain case. You will have essentially a chain that is running between two gears over here. I don't see it being used very often, but there are in some of the scenarios based on your application, the engineer may decide that in a pumping unit rather than, because of the space limitations. you may decide to, rather than using space reducers, to use a chain case. One of the advantages of chain cases, it's more reliable, it's compact. Not much to discuss in the speed reducers over here. Essentially, it's a parallel shaft style unit. Uh, what is essentially a parallel shaft style unit is that the shaft right over here in the input shaft is parallel to your output shaft, which is right over here. It is at a 45-degree angle. This is done just because the space on a pumping unit is very limited. So you have to fit it in a very tight space. So you have everything mounted at the 45-degree angle. And then essentially this will act to transfer the force from prime mover to your reciprocating pump. Fluid and components, two of the fluid and components is essentially your discharge valves, your suction valves, and your discharge lines and suction lines. One of the things about them is we were talking about what we call we were talking about air vessels and how we can ensure that there are no overpressing kind of a situation. So on the suction side of this manifold, you will have what we call we are going to see it in the coming slides, but essentially there is a rupture disc. That is to ensure that if there is any overpressure situation during the suction of the pump, then you will have some sort of a relief or a discharge, or like an emergency discharge, so that it does not damage the pump, because there's a potential. One of the things about the reciprocating pumps, which makes them very different from the centrifugal pumps, is that if there is a blockage in the line, whether it's a discharge line or suction line, the pump will continue pumping, will continue developing that differential pressure until something gives way. So you have to have these either rupture disc, pressure relief valves, or some of these safety features built inside your pump to ensure that if there is an overpressuring situation, if there's a blockage, if there is something which is not working right, you will have some sort of a pressure relief, because if it's not, it's going to blow up the power end. And then essentially what you see over here is that this is your suction valve seat, this is your discharge valve seat. Once your the plunger will move up and down, the fluid will enter from the bottom in the left stroke, and in the right stroke, the valve will seat and the suction port will be closed, and then your discharge cover will be open, and your discharge valve will be open and can pass this one. We were talking about the pressure relief devices for these pumps. One of the safety features that is built right in the suction valve. What you can see over here is a cross section of the suction valve and its discharge valve. The only thing that makes them different is a small red piece over here, which is called what we call a rupture disc. The valve will be ruptured if there is an overpressuring situation. This is to ensure that your treating equipment and your power end is protected from any damage due to accidental or violent overpressure of the fluid end. The valve will be ruptured. This will let in the loss of sealing, which to prevent any adequate suction and prevent the pumping chamber from developing any pressure. So if your pump is not developing pressure, one of the first things that they will check is to ensure that the rupture disc on the suction valve is not damaged. You cannot interchange, and this is written right in red over here, you cannot interchange your discharge valve and your suction valves, just because in the suction valve you have this rupture disc and you don't want that to go on the discharge valve. Essentially, you don't want discharge valve to go on your suction valve because you won't have that safety feature. This is just a 3D screenshot of a lubrication system which I picked from one of the pumping units. This is to ensure that your lubricating oil is going to the places where it should go. And what are those places? Those places are your bearings, your seals, and everything in between. So it will extend the life of your seals. It will essentially extend the life of your plungers. So clarity and the quality of the lubricating oil is very paramount. That's why we have usually testing facilities right on the oil and gas pieces, which will ensure that you are testing this oil at certain intervals to check if there is any water ingression or if there is any uh, uh, contaminants in there. And then there is a PRV that is mounted right over here, right at the very top, to ensure that there is no overpressure kind of a system. If there is any air that is inside the system, that it can be properly ejected. And there is only optimal level of air pressure that is present in the tank. We were talking about different type of pumps. The cementing pumps, you can see right over here, smaller pumps compared to stimulation pumps. Usually these are triplexes, usually, not always, but most of the time in the cementing unit, what you will see is that it's a triplex kind of pump. You can see the gear reducer right over here mounted at a 45-degree angle. One of the ones which you will see right over here, this is particular model of pump with a chain drive rather than a gear reducer. Then if you go to the stimulation services where this is where your very high pressure pumps will come in. You can see one example over here, which is a 20-plex, which is a 5-chamber reciprocating pump. The reason for that is stimulation services are being done at a very high pressure, usually at 10,000 or 15,000 psi. So these pumps are usually bigger, they have bigger cylinders, they have more cylinders. And then essentially most of these would require some sort of a gear reducer rather than a chain drive. One of the concepts in the reciprocating pump is called a slip of the reciprocating pump. Simply, it is a difference between the theoretical discharge, which you will calculate through your formulas, and the actual discharge, which you will calculate through a flow meter. And the slip will determine kind of like your efficiency of the reciprocating pump. You want as less slip as possible. So you try to bridge that gap as much as possible. You can see the formula right over here. It's a very simple percentage formula, which is your Q theoretical minus your Q actual divided by Q theoretical. And then the Q actual divided by Q theoretical, or this flow rate actual divided by flow rate theoretical, is your coefficient of discharge, which is called CD, right over here. There is something which is called, it is not very common. I have never seen it, but it is present in the test book, which is called a negative slip. A negative slip is essentially a concept in which your actual discharge is more than your theoretical discharge. Normally it doesn't happen. Your actual discharge is always less than your theoretical discharge because there is a fluid slip which usually happens between the suction valve and the discharge valve. Because as much as we want everything to seal perfectly, perfect sealing is a lot of times doesn't happen, actually happens. Negative slip occurs in a very particular situation where you have a very long suction pipe, or your delivery pipe is very small, or the pump is running at a very high speed. As I said earlier, usually the pumps do not run at a very high speed just because we don't want them to run at a very high speed. They essentially want pump to run at a moderate speed of maybe 500 RPM, 600 RPM. So negative slip is a very, very, very rare phenomenon. Some of the advantages and disadvantages of the reciprocating pump. Throughout the presentation, I've talked about the advantages, but we can summarize them over here. You can actually have a high pressure that can be obtained at the outlet. It's not a self-priming pump, or it does not require it does not require priming. It's a self-priming pump. That means you can have a suction line which is completely empty and it will fill it up with the fluid. So very similar concept is also used in reciprocating compressors as well, which with similar construction, similar. So it can be used for the air, although I would never recommend to use it with the air. It can run dry. It can be used to compress air, but reciprocating pumps are not the ideal equipment to compress air. Use reciprocating compressors. They are spec and they are built to that. Some of the disadvantages, I alluded to this earlier as well, very high maintenance. They are reliable, but compared to centrifugal pumps, they are not that reliable. Uh, Low flow rates. Essentially, this pump is built for high pressure, not flow rates. So you with high pressure, you kind of compensate or kind of compromise on the flow rates. They are big, heavy, and bulky. Uh, these are very heavy. The power end of fluid ends. These are casted and forged components. So essentially, they are bigger in size. And obviously, these come with a very higher initial cost. With premium seals and packings, the cost is usually very high for these pumps. They are used in the oil drilling operation. So apart from stimulation and pumping, one thing that I forgot to mention is that they are also used for pumping mud during the drilling operations. So you will see it on the oil rig quite often. And then they are used for pumping, like battery pumping or pumping the fluid from the well to a separation facility as well. Not very common. We usually use centrifugal pumps for that. And then they can be used as small boilers, condensate return pumps, or as a dosing pumps in the chemical facilities. Essentially, this is my last slide. So thank you very much for patiently going through the presentation. We can take some questions now.
Okay, we have a question from Stelio.
Hello, good afternoon, Dr. Lambert.
Good afternoon.
Good afternoon, everyone, and good afternoon, the presenter. And congratulate once for the presentation, and say that it's a pleasure to see your presentation because I'm learning a lot every time. Okay, thank you. Okay, the first question is. I would like to know that we can consider the piston pumps a manual pump. Hello?
Yes, we can. Yes.
Yeah. And what about the diaphragm pump? The third one. Is
The
the
diaphragm
manual
pump. No, so
diaphragm?
the
Yes.
diaphragm pump is usually driven by like a small motor.
Okay.
Yeah.
And what is the maximum flow you can get for the piston pumps once it's a manual?
That depends upon a lot of factors. One of the factors is the cross-sectional area of your cylinder.
Okay.
So uh, we can have in the stimulation kind of services, I have seen uh, a bunch of these pumps delivering close to 5 meter cube per
Okay.
minute.
Okay.
Essentially, just because, as I mentioned earlier, that these pumps do not deliver a lot of flow rate. So what we do is that we actually daisy chain these pumps. So you will have multiple pumps connected with each other. But for a single pump, if I have to quantify, uh, 2 to 3 cubes is quite common per minute.
Okay.
Meter cubes.
Okay. Thank you. Sorry, I have more two questions. I think is Uraka. Uraka is a brand of the pump. I
Yes.
saw a video. Uraka is a brand of the pump.
Yes. Yes. There are different types of pump. SPM makes some pumps. Caterpillar makes some pumps. Yeah. So
Okay. And also the last one, please. You can back for the second slide, please. I saw a formula for to calculate the work per second. Yeah, please. So we can go back for the second slide, please.
just give me 1 second. I'm bringing that for
Okay,
you.
thank you. Thank you. Yes. I saw that formula. I see that it is ALN. What is that?
So A is your cross-sectional area of the cylinder, L is your stroke length, N is your number of revolutions.
Yes, sorry. A, it's what? Sorry.
Cross-sectional area of the cylinder.
Okay.
Yeah.
And L? L?
Stroke length. Stroke length.
Stroke length. Yes. Okay. Thank you, sir. Yeah. Thank you. Yeah.
No problem.
Thank you. Yeah.
Hello. Hello, sir.
Hello,
Hi.
good evening.
Yeah, good morning, sir. Good morning, the presenter. Good morning, everyone. Thank you, sir. Yeah, my question is this. What factors should be considered when selecting a reciprocating pump for a specific application?
Very good question. Let's revisit this formula right over here, because essentially some of the factors can be discussed right on this formula. One of the first factors that you need to consider is the density of your liquid. If you are pumping a very viscous liquid, then you need to consider something which is a bigger cylinder, for example. Then similarly, the other thing which you are trying to consider is that how big of a prime mover that you would require. So essentially, you would need to calculate your power required to drive the pump, because power required to drive the pump will help you to spec out your prime mover. So the other factor which you need to consider is the head of the pump, like how much vertical distance it needs to cover up, how much is the suction height, and how much is this discharge height. So all of these factors actually help you to spec out a proper pump or selecting a proper pump.
So Hassaan Ali, when you say the pump needs to be larger, are you increasing the area, the cross-sectional area, and the torque, the length of the piston?
Yes, essentially, yes.
Are you increasing at all the number of revolutions of the piston?
The number of revolutions you can play with it, but you cannot play with it quite a lot. The reason for that is that your prime mover, which is a diesel engine, is usually off-the-shelf component, or off-the-shelf assembly. So you will have engines which are being driven at particular RPM. You really can't change that much. Then you need to figure out that in the catalog what types of gear reducers are available. So you can
in
play
that
with your
equation, where do you see the power?
So the power is right over here, which is this work done, which is rho GH2ALN multiplied by suction height plus discharge height divided by 1,000.
Okay.
Yeah. So once you
All
know
in kilowatts.
everything is in kilowatts. Yes.
Okay.
Yeah.
So you're increasing the P. You're also increasing the A and the L. For more viscous liquids.
Yeah, so you can't really change the gravity of your liquid unless or until you have some sort of a treating facility before the pump where you can actually alter the gravity or specific gravity of the liquid. So this is usually a constant. Your acceleration due to gravity is a constant. The things that you can play with is either your stroke length, so you can increase your stroke. That means a bigger pump or a longer pump, or you can increase the diameter of the cylinder, or you can increase the number of revolutions of the system.
So to go back to Ismail's question, when you're considering what type of pump to use, is it basically just how viscous your fluid is and how much you want to pump?
Let's start with there. Yes.
Thank you, sir.
Let's go to Bibi Faziana. Go ahead now.
Hello, everybody.
Hello.
Yes, actually, I do not understand what L stand for. L in this formula.
So the L is essentially your stroke length. So the stroke length, which you can see right over here, it is twice the radius of your crankshaft. So if your crankshaft is this is the radius of the crankshaft or the length of the crankshaft. So essentially you multiply it with 2, so you will get the stroke length.
Okay. Yes, actually, where can we apply this pump? In my field, I think I work in lab, and there we use various apparatus. We have pumps in these apparatus. Is this pump reciprocating pump using these apparatus? I don't know. I just want to.
So in the lab type of an environment, I think reciprocating pump, one of the types of, let me just go back to that slide. There is a type of pump that is used in the labs quite often, which is called a diaphragm pump. So essentially, these are really small pumps.
Yes, very small.
Very small. They look like a small, like a not really a cylinder, but more like a plate.
A plate.
And they are usually in the lab or in a small working environment. They can be driven by pneumatic pressure, or a pneumatic pump. So essentially, these are very small metering pumps that are used to inject chemicals in a very precise quantities.
Yes, exactly. That's it.
Yeah.
Thank you.
Yeah.
Thank you.
No problem.
Thank you.
All right, now we go to Elvis. Hello, good day to you, sir.
Good afternoon or good evening, Signor Eduardo.
Good afternoon.
Okay, good afternoon. Hassaan Ali. Hassaan Ali, just one question here. I know I came in late. Sorry, it's like you're talking about quantum electrodynamics here. But just one question in terms of the pump you talked about. How do you control the valve? Is it controlled at one area, and how is it the power maintained on all this?
How do I
control the valve, and how do you control the power supply in all this? Is it controlled in one point or what?
So the power supply is essentially controlled by your prime mover. So your diesel engine or your natural gas engine. For the control of the valves, they are set to a point where they will open at a particular pressure only.
So the pressure is maintained in different areas. We have different source.
Yes. So let me just. Yeah. So these are spec to a point where they will open at a certain pressure only. They will not open at a low pressure. They will not open at a high pressure. There is usually a spring in between that you can change, and you can either increase or decrease your opening pressures or closing pressures.
So this is attached to a software application.
No.
Yeah.
It's not. It's totally manual at this point of time. Most of the reciprocating pumps is totally manual.
It's totally manual.
Yeah.
Okay. Thank you. Thank you, Senor.
We can take the next question.
All right. Thank you so much, Elvis. Now we go to Olufemi. Your question, please.
Okay.
We can hear you, sir.
Excuse me. Yes. Good morning, sir. Thank you. Can you hear me?
Yes.
Yes, we can hear you.
Thank you very much. I wish to thank Professor Syed Hassaan Ali for excellent lecture. So my question goes thus: what are the failure criteria for the reciprocating pumps, and what is the frequency of failure? My question goes thus: I'd like to know the failure criteria. That is, what can possibly cause failure, and what is the frequency of failure? That is, rate of failure. Now, for this, for the frequency of failure, will it require maybe a daily maintenance or weekly maintenance or monthly maintenance in order to prevent failure. And this failure rate, is it the same for the high pressure pumps and the low pressure pumps? Thank you. I don't know if you have heard me.
I did. A very good question, actually. It's a failure modes. Some of the common failure modes that you will see. So I will try to address one question first. These pumps do require a lot of maintenance. Usually there will be daily checks, weekly checks, monthly checks, and then you will have like service level 3 maintenance, in which the whole pump will be taken apart bit by bit, pieces by pieces. Everything will be inspected, and some of the things will be changed. So they do require a lot of maintenance. Usually on a stimulation services or on the cementing services, we have mechanics on site as well to maintain these pumps, just because the failure modes are quite high on these pumps compared to. Now I'm comparing this to a centrifugal pump, not to anything else. Compared to a centrifugal pump, these pumps, a similar pump will have a higher failure rates. Now, this is very subjective to say that a particular pump is high maintenance, low. It all depends upon how good your checks were, how good your maintenance was, how good the people are, and how well you are taking care of these pumps in terms of lubrication, in terms of they are not exposed to elements, whether you are checking for any telltale signs. So a lot of effort right now in the industry is going on a concept which is called prognostic health monitoring. So the prognostic health monitoring is essentially trying to figure out what are the size of this, or what are the issues.
Piston.
Hello. Sorry. So there are a lot of sensors that can actually go on these pumps to ensure that we are catching the signs. One of the telltale signs, or one of the issues that you can probably catch early on, is high vibration. So if your vibration sensors or accelerometers are actually picking up high vibrations, that means something is about to change, or something is about to fail. So this is what we call a prognostic health monitoring, where you are taking temperatures, you are taking pressures, you are measuring vibrations to figure out that when a particular piece of equipment or this pump will fail. A common failure mode is packing failures, seal failures, ruptured disc on a suction valve being damaged. Then similarly, issues with your gearboxes, issues with your power end of the pump. So these are some of the common failure modes on these pumps.